Hi, everyone. Thanks for coming to my talk. My name is Archa, and I work as an engineer at Alphabet's Calico Labs. And I'm going to be talking to you today about an engineer's perspective on reproducible ML research. So I'm very excited about talking to you all today about this topic, what it means in practice, why you should care, and a work making your work easy to build upon. As we go, if you have any questions, feel free to drop them in the chat, and I'll either address them right now or as a follow-up. So I was an engineer at Google for a few years before I got into ML, and the insights today come from applying engineering best practices to ML work. The intended audience for this talk today is a range of students to scientific researchers who may be unfamiliar with software engineering practices in both recording and replicating their work. There's a lot of depth to this topic, but my talk today will provide a high-level overview on how to think about reproducibility when doing ML work. So let's dive right in. So why should you care about the reproducibility of your research? So we want to be able to trust others' work, and we want to be able to make our work easy to trust. Without this, researchers are unwilling to build on others' work, and their research becomes insular. This slows down progress and holds us back as a community. So if our ideal is total reproducibility, how bad is the problem really right now? So let's stop here. And everyone think about what percentage of research you would realistically want to be able to consistently reproduce. Everyone actually think of a number right now. Okay? So in 2016, in a study done by Nature, out of 1,500 researchers questioned across a wide variety of fields, only about 30% were able to replicate another person's work. Let's stop and think about that number for a second. What if your search engine only works 30% of the time? Imagine you type that in, and this is what you got. Would you trust it? You wouldn't really use it much. You wouldn't recommend it to anyone, and you certainly would not rely on it for your daily work. So why would you build on research that is about this accurate in practice? Lack of reproducibility is especially concerning in machine learning, with a lot of work being done on this topic in general. ICML this year had a workshop dedicated to just this problem with a lot of great speakers. I highly recommend you go check out this page and look at these a lot of these slides that have been posted online if you're looking to do some follow-up on this topic later. So hopefully you're now convinced that this is an important problem that's worth fixing, and also one that seems very tractable. So let's go through a common ML model development workflow together. I will then talk about small improvements we can make to it to increase the reproducibility of your models. So we start with the researcher. You're working away at your lab. You have an idea. You decide to start implementing it. You think, I'll write this in TensorFlow in an IPython notebook, and I'll use this specific data set. You implement some code. You run the code. It fits a model. Once that's done, you examine the results. And maybe you're not happy yet. You go back and you modify the code, go through the process again, maybe have some back and forth. You do this a few times. And at some point, you're happy. So you publish your results, and you're kind of done with that. One day, another researcher reads your paper and has an idea on how to build on top of it. So they decide to use their own tool chain. They implement your code. In the meantime, Jupyter has replaced IPython. Everyone's moved to Python 3 from Python 2, and TensorFlow and Ubuntu have brand new versions now. So, it doesn't quite work. Despite the fact that this workflow is doing most things right, like publishing details of your implementation, open sourcing the code, it doesn't still quite come together. And so what is the cause of this problem? So there's 4 classes of problems I'm going to address today, and how they could make your work harder to duplicate, and changes you could make in your workflow to prevent this from happening. First, I'll talk about some general coding practices that'll help you build a solid baseline to stand your work on. Then I'll talk about the kind of dependencies we often have in our implementations and how to control for any variability there. The third one is about the non-convex nature of a lot of our optimization problems, especially in the context of deep learning. This becomes really important. The last one talks about the general variability in our environments. And these are often outside of our control, and how there's some statistics-based methods for controlling for this. So let's start off with coding practices. I'm going to talk about two basic principles to just get us off to a strong start. So let's revisit our workflow from earlier in this talk. In the back and forth between producing results and tweaking with our code, it's remarkably easy to lose track of which version of the code produced the desired results. And a version control system like Git helps us keep track of all the changes we make and prevents us from losing work. And for those of you who happen to be less familiar with Git, a really great starting point is GitHub Desktop that makes it super simple to commit and push changes and host your repository on GitHub. And if you use version control less than you'd like, I highly recommend this tool. And I just want to reiterate this. Version control is totally invaluable. Learning how to use it is a one-time investment, and that makes saving your work incredibly easy, basically forever. You'll see later in this talk why version control is especially useful in ML, and I'm going to talk a little bit more about specific use cases. So the second thing I want to talk about is modular development. Creating layers of abstraction is a very powerful idea. It allows us to create incredibly complex applications using programming languages, which are built all the way up from applied physics. But this only works if every layer is well tested and self-contained. So if you're building a complicated piece of code, think about this picture and how you could split up your code into different layers of abstraction, and you should implement and test each one separately. So you don't have, say, a memory leak in one part that causes non-deterministic behavior in your overall system, and you only really catch it when you run everything end to end, at which point it's basically impossible to debug. Okay, so that's it for coding practices. Let's talk about dependencies. So what is a dependency? Any part of your system that you did not implement yourself counts as a dependency. Some of these are obvious ones that you'll immediately identify, like TensorFlow or NumPy or scikit. But there's more subtle ones that we don't often think of, like the Python language itself and the hardware and the OS you're running your code on. The specifications of all of these often affects how our system behaves in very subtle ways, so it's important to just keep them in mind and be aware of them. To make it easier to think and reason about them, dependencies can be split into three basic categories. Software, which is like a TensorFlow, scikit that we just talked about. System software, which is basically the operating system you're running on. And the hardware, which is like your GPU, your CPU, the drivers for each of these. So now the reason I'm actually talking to you about all of these is that they change more often than we sometimes think. Each new version of any of these dependencies brings hundreds of lines of code that your system is now interacting with. There's some fairly simple ways to control for these, though. So let's talk about software dependencies. These are the packages you install. You want everyone who runs your code to have the exact same version of every package you had when you ran it. But first, you need to isolate them on your own machine so you can keep track of which ones you actually used. For Python, there's some very handy tools, some of which you might be already familiar with. You probably already know about pip, which is great to use to install packages like TensorFlow. Virtualenv is great and it lets you create an isolated environment in your box where you install only the dependencies you need for a certain project. Once you're done implementing all of these, you can use something like pip freeze, which just lists all the installed libraries in your current environment. And you can include this list in your code repository so everyone knows how to run your code correctly exactly. And I know I'm mentioning some tools here, and I'm going to talk about a few more later, but I just want to point out that's not the focus of this talk, and it's not meant to be a tutorial on how to use these tools, but rather the general idea of what kinds of tools to use and an illustration that such tools exist. Okay, so this is the world we're going for. Not for machines to take over the world, obviously, but for us to be able to create easily replicable environments. So every run of your project is exactly the same. Of course, we can't control everything about how someone runs your code. And that brings me to my next point. You can't ask someone who's going to be using your work to run it on the exact same machine as you. I mean, we can tightly control software often, to a certain extent at least, but we can't do the same for hardware. But we can document exactly what we used. So if people are debugging issues later on, they know exactly where to look. So in your implementation details in your paper or in your repository, you can include the operating system and version you used and the hardware you ran it on. And again, there's some specific commands for some specific use cases. The first one here tells you which exact version of Linux your machine is running. And the second one prints out all the details about your NVIDIA GPU. And if these specific ones don't fit your use case, I really encourage you to find the commands that do fit your specifications, at which point the documentation for this becomes as easy as copying the output of these into your repo's README, and you can just have that as part of your setup script going forward. All right, so let's talk about non-convex optimization and the issues that might be around that. In traditional ML methods, we care a lot about keeping our optimization spaces convex. There's generally only one place you can end up in at the end of the hill. There's a lot of nice loss functions that have this property, and that makes our life a lot easier. However, especially in deep learning, we're almost always working to optimize our losses in very high dimensional and extremely non-convex spaces. In these spaces, you can end up in a lot of different end results, no matter how long you train for. So even if someone runs the same exact algorithm as you on the same data set as you, they might end up on a totally different local minima or get stuck in a saddle point and mark your research as something that they could not reproduce. So while there's nothing we can do to get past that mathematical truth, there's some things you can do to make it a little bit better. And we've already talked about version controlling a little bit for your code and having a Git repository for each version of your model, even if it does something slightly different. Here, I'm proposing doing the same for the actual weights learned by your model, for the actual parameters you infer, and tightly coupling each version of the weights to the version of the code that generated them, and marking them as such in your commit messages and so forth. This way, someone using your work can start with the exact code and model you report in your paper. And here's some code pointers to get you started. In TensorFlow, there's a lot of excellent support on how to save and reload your models at any point. The weights are written to disk, and in most cases, they're small enough that you can just include them in your repository, and it's super easy to keep track of. In something like scikit, you can use pickle to just dump your weights to a file in the same way, and scikit actually supports reading them back from that pickled file directly. Additionally, just reporting your weights isn't the entire picture, because if you think about walking up and down a non-convex space, the way you take your steps is also going to change where you end up. And this is why picking the right optimizer is crucial for getting a deep learning model to train in general. So someone could use your model in your code and run stochastic gradient descent instead of momentum, and then end up not training on their data set at all. So document the optimizer you used along with the weights that it produced and the code that actually you used to produce it. And it's worth noting here that this is equally important for the parameters you train as well as the hyperparameters. And you want to kind of report both, and if there's different optimizers for both, report those as well. And let's take a minute to just talk about random variables. So in almost all ML models, there is some random initialization that you do. A very common example is using Xavier initialization before you start training your deep learning models. Here, it's important to remember that random number generators, as they're implemented in modern programming languages, are never truly random. They use a seed value to start sampling from the underlying random distribution. So unless you specify a seed, most generators will use something like the CPU clock, and the results look mostly random. And this is kind of a pain. So most people will often seed their generators, so multiple runs of their code have the same kind of randomness. And in incredibly non-convex spaces, little differences in this initial seed can lead to wildly different results. The same way using a different kind of initialization for your parameters leads to wildly different results. For instance, instead of using Xavier, if you initialize to all zeros. So it's really important in this case to always seed your variables, but also include what seed you used with your code so people can reproduce that same behavior. The last point I wanted to cover today is about environmental factors that often tend to be outside of our control. You can think about so you're often you're probably used to thinking about this in terms of reinforcement learning, and you think of this as the underlying stochasticity of the world you're running your simulation in. So, if you take the same action from a state 2 different times, you might end up in 2 totally different states, depending on the underlying properties of this world. And this is applicable even outside of reinforcement learning, and it specifically comes into play if our models are being used to influence the real world in any way, or if you're working with the real world. Like, for instance, if you're training a model to optimize an assembly line workflow, or you're training a model to optimize pickup routes in a ride-sharing service. You can't control all the variables that will exist in the real world. So you have to kind of build that robustness into your data sets and in the models, in the training process you use. We can turn to some great statistical methods for this. Statistical Power is a great tool. It helps us calculate the number of trials we need to run for an experiment before we can say anything with certainty about the results. So for instance, in RL, you can ensure your model is robust by doing this calculation to determine the number of times you need to run your trained model before you can confidently report the test performance with it. In a similar vein, we can also use confidence intervals. Now, confidence intervals are important as long as they're not too large, like in this comic here. But so if you do these calculations, you can directly quantify how sure you are about each result you're exposing. And understanding this is crucial to determine whether your result is ready to be shared, whether you should be working a little bit more on it, and also for people to have realistic expectations about your work and understand what exactly its limits are. So there's a few thoughts I want to leave you with. The methods I've talked about today are very specific and they're non-exhaustive. And as our field evolves, they will become less relevant. So I want to talk to you about a high-level framework for thinking about this problem in general going forward. So training ML models is a very practical art. You all, I'm sure, understand that the process is mostly driven by instinct. Every time you tweak a model, you're usually building on all the experience that you have had in the field in the past. The problem with instinct is that it's very hard to identify, and it's even harder to teach. When people are kind of missing this ephemeral context and they try to replicate your work, things will often get lost in translation. When we have key ideas that move our work forward, we can never say why we have them. And this has always been true of all scientists. So what do scientists generally do? So as you go through your work, document those ideas as you have them. Document what that idea led to. Document what were the conditions right before that made you think about it. This is analogous to a scientist keeping a journal with field notes. And right now in today's world, this means committing all your code as you go along and saving all your models and all these things I talked about. But the general idea that's underlying all of this is not just to share the results, but the process that got you there as well. And that's all I have. So thank you. I can take some questions right now. So there's one about TensorFlow and common technologies like that. So TensorFlow is actually huge for a lot of folks who are doing deep learning in industry. It has immense support and has a great community around it. I did a little bit of comparative research when I first started getting into it, and I originally started with Keras. But the community around TensorFlow is growing much faster. For more traditional, also, I definitely recommend that, but things like Keras and Theano are very big for deep learning as well. For traditional methods, a lot of people use either homegrown platforms or things like scikit. Yeah, so there's usually a few issues. So I'm answering any issues with TensorFlow across platforms, things to watch out for across Linux, OS X, and Windows. The short answer is no, but with caveats. So just in most cases, and in the most general case, it will work. But while that's true on paper, I never actually do that for my daily runs. If I'm going to be running a platform on Linux, I'm sure as hell going to train it on Linux as well, just because there tend to be sometimes like very tiny things like how C stores structs on disk that change something slightly about your code and you end up with non-deterministic behavior. So it's usually fine, but your mileage may vary. So I'm answering, I was a little curious if you have a workflow for saving the weights file, which can get large, and how to version those as well. Right, so I talked about how you can store weights in your GitHub repo, and that's going to be fine for most people unless you're using you're training on huge deep learning networks and you have a lot of parameters, in which case you can't realistically host that to GitHub. The most common use case for something like that is to version these directories on your disk and host them somewhere on a private server for people to be able to have access to. Most universities and labs have private servers like they set up, and you could selectively expose some of these files. So I was a little curious to have a workflow for. Oh no, I already answered that. So I'm answering Leah's question. You have documenting the process that leads to a particular model. Did I have any specific tools or process in mind? So this is, so I'm assuming this is about the last part of my talk where I was talking about the process, the intuitive process. This is meant to be, honestly, it depends on what works for you. What works for me is just having some sort of notes where I write down what I'm working on at any given point, and when important things happen, I note them there. And that's not meant to be shared as such, but it's a way for you to understand what the inflection points of the process were for you. And so when you're publishing a paper or writing a blog post, however you're sharing it, you can go back to it and understand, and then you know which points were non-intuitive and which points to explain a little bit better when you're communicating your ideas. Next question is, are you a fan of Docker containers? I'm a huge fan of Docker containers. Docker containers are awesome, and you should definitely use them for production deploys. They sometimes, if in this specific context, they might be a little bit of an overkill sometimes, unless you're expecting to run long-run production servers. The isolation of the runtime environment doesn't always come in handy unless you have multiple processes running on the same computer at the same time that all have different dependencies. If you're just going to be running one thread at a time, you can very easily just work with a virtual environment. If not, and you're going to be persisting processes for a long time, Docker containers are great. How about peer programming for ML? Peer programming for ML is, I haven't done a lot of it, to be perfectly honest. Peer programming in general is great, and working with people, particularly in something like ML, is very nice to be able to be able to have someone to bounce ideas off of, especially in the planning process. The problem with and the reason peer programming works great is that you get a lot of feedback right away, and one person can be writing code, if the other person gets tired, and you can kind of bounce off each other's ideas. The problem with doing this for deep learning or for bigger ML models is your feedback loop isn't so fast. So I don't know how well that would work, but peer brainstorming is probably fantastic for ML. Do I follow Google style guides religiously? Depends on what I'm doing. If I'm writing production code, I will almost definitely follow Google style guides. And working within Alphabet also definitely adds to that. Everyone sticks to them. And the thing with style is that you want to be consistent above everything else. So if you're within the Google ecosystem, that's following Google style guides. For personal projects, I'm probably not that religious about it, but it tends to get a little bit ingrained after a while. And I think specifically for things like Python, like things like the Pepe style guide, or a lot of them just make a lot of sense. And once you get used to it, you kind of just do it forever. What does the environment for my pet project looks like? What GPU do I use? So I use TensorFlow and I tend to host on either private or public repos on GitHub. I use Python and a hosted Jupyter server on my personal laptop. My GPU is a GTX 1080 that I also use for gaming. So it works out nicely. If that's all the questions, I'll sign off. You guys have been great. Thank you so much, guys.